Did you know that in many industrial processes, there is a waste of energy or a heat stream that is being exhausted? Well, heat exchangers can be used to recover this heat and put it to use by heating a different stream in the process. This practice can save a lot of money in the industry and protect our environment. This is Vanya Shaukat, and me along with my groupmates Muazzam Aziz and Shahriar Shahid will explain the stability of heat exchangers with delayed boundary feedback. So, why we need heat exchangers and where we have seen heat exchangers. The most common application of heat exchangers is not really far away from us, that is, in our homes, refrigerators. They play a significant role in the process of refrigeration. Heat exchangers are also used in wastewater treatment to maintain the optimal temperatures. In commercial aircrafts, heat exchangers are used to improve fuel efficiency, which has a big impact on economical side. They are widely used in process cooling, power electronics and automotives. After having this quick little review about the heat exchangers and why they are important, let's move to our Hideki Sano's research paper in which we analyze the stability of heat exchangers with delayed boundary feedback. Stability is considered to be an important property of a control system. More specifically, we can say that stability allows the system to reach the steady state and remain in that state for that particular input even after variation in the parameters of the system. In case of aircrafts, we need to keep the stability of turbines steady. Heat exchangers of both counterflow type and parallel flow types are treated, where they are respectively described by a coupled hyperbolic equation with time lags in the boundary feedback loop, which will be discussed further by my groupmates. In this paper, it is shown that the upper bound of the feedback gain to assure the closed loop stability is solved by computing the edge norm of a complex function under the presence of any time lag. That is, each closed loop system with admissible feedback gain is robust with respect to any time lag.
Now let's discuss the types of heat exchangers. Heat exchangers are typically classified according to the flow arrangement and type of construction. The simplest heat exchanger is one for which the hot and cold fluid move in the same or opposite direction. This heat exchanger consists of two concentric pipes of different diameters. One of the arrangement is known as parallel flow arrangement. In the parallel flow arrangement, the hot and cold fluids enter at the same end, flow in the same direction, and leave at the same end. The second arrangement is called counterflow arrangement. In the counterflow arrangement, the fluids enter at opposite ends, flow in the opposite direction, and leave at opposite ends. Now let's discuss the concept of stability, what stability really is. The stability of a control system is defined as the ability of any system to provide a bounded output when a bounded input is applied to it. More specifically, we can say that stability allows the system to reach the steady state and remain in that state for that particular input, even after variation in the parameters of the system. Stability is considered to be an important property of a control system. It is also referred as the system's ability to reach the steady state. As it is an important characteristic, thus the performance of the control system shows a high dependency on stability. We have already studied about the control system, that the various units of the control system combinedly operate so as to provide a specific output of the system. In order to get that specific output, the various parameters of the system must be controlled. Along with this, the system must be stable enough so that the output must not get affected by the undesirable variation in the parameters of the system or disturbances. Thus, we can say that a stable system is designed so as to get the desired response of the system without any intolerable variation with the changes in the system parameters. Now let's have an overlook on the theory of stability analysis. Analysis is the theory that characterizes the stability of the equilibria of a dynamical system. It is a key principle in fields such as mathematics, biology, engineering, and system control, where analytical methods are regularly used to study the properties of dynamical systems. The goal of stability analysis of time delay system is to determine the region in the delay parameter space at which the system is still stable.
Now let's move on to the mathematical approach of our project as per the research paper. The work started on the characteristic equations with delay boundary feedback for both types of heat exchangers, that is, counterflow type heat exchanger and parallel flow type heat exchanger. In these equations, L represents the length of two tubes, V represents the fluid velocity, while H is the rate of heat exchanger and K is the feedback gain. Tau here is the time lag, which is kept greater than 0. Later on, variable transformation was performed on these equations in order to obtain exponentially stable C0 semigroup, which is a strongly continuous one-parameter semigroup. Then, Hilbert spaces were formulated in order to satisfy the condition which is highlighted here. If this condition is satisfied for any time lag, that is tau greater than 0, then we have exponentially stable system for any time lag as shown here. Now let's move on to the simulation results that we got by applying this approach. These simulation results are for counterflow type and parallel flow type. These simulations are comparison between solution of open loop system and closed loop system with delay. These graphs are plotted for tau, time lag, L square norm, and T, time. The conclusion that we draw from these graphs is that closed loop is more stable as compared to open loop, but it cannot enhance the stability with open loop system. Next, we have the simulation result on the basis of feedback, that is positive feedback and negative feedback. Here we have kept the K magnitude constant and the tau is 0.1 and 7.5. But here one thing is to be noted that the magnitude of K is same, but one is positive and the other is negative. These graphs are for both counterflow type and parallel flow type. The conclusion that we draw from these graphs is that negative feedback is more stable as compared to positive feedback. Now let's we have the conclusion. Our main objective was to have the stability analysis for heat exchanger with delay boundary feedback. In past, many scientists work on this project, but they fail to obtain the data for any time lag. Here we examine the stability with delay limit feedback for the two types of heat exchangers. Overall conclusion of our project is closed loop systems are exponentially stable and delay free with the system feedback benefits. That's all from our side. Thank you.